Top of the morning to you. The sun is out and shining, and we're going to continue our discussion of nuclear science. Last time we talked about nuclear decay reactions that lead to radioactivity. We talked a little bit about what determines the stability of nuclides, and we defined a half-life and talked about what we mean by an exponential decay and why there exists different half-lives. In this lesson, we're going to talk about additional nuclear reactions, in particular fission reactions and fusion reactions, and talk about their importance. A nuclear fission reaction is one in which a heavy nuclide, that is one of the big guys, is split into two smaller, lighter nuclides. And generally energy is released when this happens. An example of this is written at the bottom of the slide with californium-252. Yes, there is an element called californium. Guess where it was created. The californium-252 can be split into barium and to molybdenum. That's not Missouri, that's molybdenum. So this is an example where a heavier element, californium-252, is split into two smaller nuclides, barium and molybdenum. Now we'll be talking about fission and fusion, and one way for you to keep these straight is that with fission, notice that there are two S's, and I like to tell students that if you think about fission as drawing a line between the two S's and splitting them apart. Now this term fission actually was borrowed from biology, and we will talk about cell fission later. So fission means splitting, draw a line between the two S's. Now, when we talked about kinds of nuclear reactions, we said there are decay reactions and other groups of reactions that we might lump together and call transmutations. And a transmutation reaction is typically one in which a scientist tries to collide some small nuclear particle with a larger nuclide to see what happens. It's a type of thing that nuclear physicists do a lot with cyclotrons and linear accelerators. Collide things together and see what can be formed. In the very early days of this type of experimentation, a scientist known as Enrico Fermi, very famous scientist in Italy, was trying to see if he could create larger elements by colliding smaller atoms or smaller atomic components with larger atoms. An example of what he was trying to do is shown in this slide, where uranium-238, he was colliding uranium-238 with neutrons being subatomic particles. And he expected to form uranium-239. However, this didn't exactly work out. He didn't form uranium-239. And then others, Lisa Meitner, Otto Frisch, Fritz Strassmann, and Otto Hahn, working in Austria and Germany, repeated his experiments and realized that we're talking about the mid to late 1930s. They repeated these experiments and identified the products that were formed. And they found that instead of forming a bigger nuclide, which Enrico Fermi had expected, that the uranium-238 was actually split into two smaller nuclides, two smaller elements, barium and krypton. Plus 3 additional neutrons were generated. And as we'll see later, energy was produced. Well, it took these scientists and others a year or two to sort of put the pieces together, and it was an interesting story involving scientists in various countries, England, United States, Germany, Italy. But when they did analyze the data and realize what it meant, it was very shocking. What they discovered is that when you bombard uranium-238 with neutrons, you split it into two smaller pieces. Rather than forming a bigger nuclide, you form two smaller nuclides, barium and krypton. Plus 3 additional neutrons were generated, plus a lot of energy. What we now call a nuclear fission reaction. Now, scientists from various countries, Italy, Austria, Germany, and England, and the United States, began analyzing these data, and they realized that they had something very powerful here. And the possession of this knowledge and any technology developed was very important, plus who controlled this knowledge and technology, because remember, in the 1940s, World War II was taking place. In the next slide, I'm going to show you what many people consider to be one of the most important letters ever written. This is a letter from Albert Einstein to Franklin Delano Roosevelt, in which he says this phenomena that has been discovered by physicists could lead to the construction of bombs. And it is conceivable, though much less certain, that extremely powerful bombs of a new type may be constructed. And he further explained in the second page of the letter that the United States did not have very much of this uranium, and they needed to work with other countries to obtain this uranium, and that a large research project needed to be developed involving university scientists. And notice at the bottom, signed by Albert Einstein. Now, actually, this letter was written mostly by another physicist, Leo Szilard, but since Albert Einstein was so famous at this time, they wanted to use his clout to get the letter to FDR, and of course, and Einstein very much agreed to use his name to help with this cause. What followed then were projects with names like MAUD, which was the military application of uranium detonation, and the Tube Alloy Project. These were out of England, and the Manhattan Project, and the cooperation between these countries, especially England and the United States, in developing the nuclear bomb. And of course, the rest of that is history. The detonation of the bomb over Hiroshima helping lead to the end of World War II. Now, what is it about this type of nuclear fission reaction that led scientists to realize that it was a very, very powerful reaction? Well, this shows what can happen. When a neutron is fired at uranium, it will cause the fission of uranium into two smaller nuclides, two smaller elements, barium and krypton. But remember that it produced 3 additional neutrons. These additional neutrons could then strike other nuclides of uranium-235, leading to their fission into krypton and barium and more neutrons, etc. And that is, essentially, you would have a chain reaction that would be an explosive reaction. Now, it turns out for this type of chain reaction, this type of explosive reaction to take place, you have to have what is called a critical mass. That is, the uranium ore that we find in the earth is less than 1% uranium-235, less than 1% of that particular isotope. Most of uranium is uranium-238, which is not fissionable in this way. To obtain weapons-grade uranium, it has to be enriched in uranium-235. You have to enrich uranium to at least about 3% or higher in uranium-235 for it to be fissionable. Actually, weapons grade is considered something like 20% or higher enriched in uranium-235. And you probably know that the development of techniques to enrich uranium took place in Oak Ridge, Tennessee. So in addition to being a chain reaction, why do these reactions release so much energy? Well, to help us with that, we turn again to Albert Einstein. We pretty much are comfortable with a concept of conservation of mass. That is, mass is neither created or destroyed. We've probably told you that, and that applies except for nuclear reactions. Because when a nuclear reaction takes place, there can be a conversion between matter and energy. And this basically is what is meant by this equation, this very famous equation derived by Albert Einstein, E equals mc squared. Now, the c in this equation is the speed of light. The speed of light's a large number. You square it, it becomes even larger. So one way to look at this equation is to say that matter and energy can be interconverted or have some equivalency, but that the amount of matter must be multiplied by an extremely large number, the speed of light squared, to get the equivalence in energy. Or in other words, that a little bit of matter is equivalent to a very, very large amount of energy. It turns out that we know pretty precisely the mass of an individual proton and the mass of an individual neutron. But when you combine a proton and neutron to form the nucleus of even the simplest element, let's consider helium, which has 2 protons and 2 neutrons. When you bring them together to form the nucleus of an element, the mass does not add up. That is, the mass of the helium nucleus is a little bit less than the sum of the components. It's a little bit less than the sum of the mass of 2 protons and 2 neutrons. Some mass is lost when the neutrons and protons come together to form the nucleus. A mass deficit. This mass deficit is attributed to a small amount of matter being converted to energy when you assemble the nucleus, forming what we call the binding energy, the energy that holds together the protons and the neutrons in this nucleus. In some sense, it's the glue, it's the binding glue that holds together the protons and the neutrons so they don't fly apart. But conversely, if the nucleus were to fly apart, as happens in these fission reactions, this binding energy would then be released as an exothermic reaction, producing large amount of energy, which can then either create an explosion or can be used, if harnessed, to produce electricity. It turns out that nuclear energy is a very energy-rich form of fuel. To give you an example, in order to generate enough electricity per day for a city of about 1 million people, it takes 4 to 5 million pounds of petroleum fuel, whether that's coal or oil. 4 to 5 million pounds, which is about 2 million kilograms. It would require only about 50 kilograms, that's about 110 pounds, that's about how much maybe you weigh 110 pounds, I maybe weigh 50 kilograms, about 110 pounds of uranium in order to produce enough electricity for a city of 1 million per day. So 2 million kilograms of petroleum fuel produces as much energy as just 50 kilograms of nuclear fuel. So in other words, the nuclear fuel is about 50,000 times more energy dense or more energy rich than fossil fuel is. So this is basically the reason why nuclear reactions can produce electricity and why there is interest in this. In the United States, we produce about 15 to 20% of our electricity using nuclear power plants. And this actually is a fairly low percentage compared to other countries. France, for example, produces about 80% of their electricity using nuclear power plants, and Japan also a very high percentage. So let me ask what may seem to be a strange question. What's the most stable element in the periodic table? Well, it turns out that it's iron, and let me explain. Larger elements want to split apart, want to undergo fission reactions to form smaller elements. That's basically the reason why we have these nuclear fission reactions. But also, smaller elements, the ones at the beginning of the periodic table, smaller elements want to fuse together, want to join together to form iron. So larger elements split apart, fission, smaller elements combine together, fusion, all trying to approach the most stable element in the periodic table, iron. So what we've defined is something called a nuclear fusion reaction, in which smaller elements combine together to form something larger. Now this is actually what happens on the sun. So one reaction that occurs on the sun, there are other nuclear fusion reactions, but one is 2 nuclides of hydrogen. This actually would be the deuterium nuclide of hydrogen combining together to form helium. When that happens, also energy is released. So a nuclear fusion reaction. This happens on the sun. And you'd say, well, why don't we use nuclear fusion reactions as a source of energy instead of nuclear fission reactions? There's one big problem, and that is that for a nuclear fusion reaction to be sustained, the temperature has to be about 100 million degrees centigrade. And that becomes a technical problem of achieving such high temperatures here on planet Earth in any kind of container. All right, so in this lesson we've talked about nuclear fission reactions and nuclear fusion reactions. We're going to pause, take a little quiz. And in this next lesson we'll talk about a number of other applications of nuclear reactions. See you then. Sun's still shining. sun's even radioactive.